Hello and welcome to video 1. In this video we'll be looking at notation, primes and the product rule for counting. First of all, you need to be able to order positive and negative integers, decimals and fractions. To be able to do that, you should be able to convert between them, and we'll go through that now. So an integer is a whole number. A whole number such as 2 can be written as a fraction by just putting a 1 underneath, which is fairly simple. If we were to convert 2/3 into a decimal, you would have the 2 here and the 3 here, and potentially some zeros after the decimal point. 3 goes into 2 0 times, 3 goes into 20 6 times, remainder 2. Then it goes into 26 times again, and this will continue to give you 0.6 recurring, which is approximated to 0.67. If we were to have 0.584 and we wanted to convert this into a fraction, then this can be seen as 584 over 1000, because 1 can be expressed as 10 over 10, 2 over 2, 300 over 300, or quite simply 1000 over 1000. If we had a top-heavy fraction such as 150 over 25, that's a 5, we should be able to divide it normally, so 150 divided by 25. Well, the bus stop method will not be very useful. We could use the chunking method. Chunking method says, let's say that we have 4 times 25, we know that's 100. Take it away, we have 50 left, that's 2 times 25, 50, 0. Now the 2 and the 4, add them, it gives 6. So that is equal to 6. Apart from that, this is key stage 3 stuff. Next, we need to be able to use the following symbols: equals, does not equal, less than, greater than, less than or equal to, greater than or equal to. Equals is fairly simple. 2 equals 2, 3 equals 6 divided by 2, 7 equals 0.7 times 10. Does not equal is simply the opposite. 2 does not equal 3. 2 times 2 does not equal 5 divided by 2. This one, the less than sign, is again fairly straightforward. 3 is less than 5, 0.6 is less than 4 over 5. This is the opposite of less than, so greater than. 4/5 is greater than 0.6. Again, the less than or equal to sign is quite straightforward. Say we have x is less than or equal to 3. If we know that x is a positive integer, then that tells us, well, it can't be 0 because 0 isn't positive. It can be 1, it can be 2, or it can be 3, because it can be less than or equal to 3. Similarly, the greater than sign, if we have x is greater than or equal to 4, and we know that x, for example, is less than 7, we know that x can be 4, because it's greater than or equal to 4. It can be 5, can be 6, but it cannot be 7, because we know from the other sign, the less than sign, we cannot take the value of 7. More of this will be covered in the inequalities chapter. Next, we need to know how to apply the 4 operations. So that is addition, subtraction, multiplication and division. This is key stage 3 stuff, now we'll not go through it. Next we have place value. Place value is interesting. So if we have 300,000 times 0.06, well, that wouldn't be easy to calculate straight away. Usually you'd look at the place value. The place value can be seen as this. So this 3 represents 100,000. So this thing is the same as 3 times 100,000. This multiplication sign stays there. Now we look at the 0.06. 0.06 is the same as 6 times 0.01. 0.01 is the place value of the number, the digit 6. Now, we know that in multiplication, the order doesn't matter, so we can rewrite this as 3 times 6 times 100,000 times 0.01. And this 0.01 can also be written as 1 over 100. So now we can say 3 times 6 times 100,000 divided by 100. And remember, the zeros cancel out, so that's 1 0, that's a second 0. So now we have 3 times 6, which is 18, times 1000, which is 1000, and that is equal to 18,000. Similarly, you can do that with division, just as I have done here, and apart from that, fairly straightforward. Now we're going to look at the priority of operations. Generally speaking, BIDMAS is a good acronym to use. It stands for brackets first, then indices. Indices are another word for powers, so like x to the 4, that is your indice. Division, multiplication. Now, division and multiplication have the same priority, so you can do multiplication then division. You've got addition, and finally subtraction. Now again, addition and subtraction have the same priority, so you can do subtraction then addition. It will not matter. Now an example is 2 times 3 minus 4 all squared minus 4 over 3. Now, first of all, we do the brackets, and inside the brackets we have this bit. Now, inside the brackets we can apply BIDMAS again, and if we apply it again, we know that this multiplication happens before this subtraction. So we can rewrite this as 2 times 3, which is 6, minus 4 squared minus 4 over 3. Now, next we go back to the brackets because we haven't finished. We only have one operation inside the bracket, and that is subtraction. 6 minus 4 is 2 squared, and then we have the minus 4 over 3. Now we have no brackets. Our next operation is the power here, and the power here, 2 squared, is 4 minus 4 over 3. Finally, we have a subtraction. Let's find a common denominator, so 12 over 3 minus 4 over 3, which is equal to 8 over 3, and that is your final answer. A quick note, the reciprocal of any term is just 1 over that term. So for example, the reciprocal of 3/5 is 1 over 3/5, which is equal to 5 over 3. Essentially, with fractions, you just switch them around. If our number is 3, then the reciprocal is 1 over 3. And I should have an arrow here rather than an equal sign, because that is not true, obviously. The reciprocal of a fraction, of a decimal, well, it's easier. Well, you can use a calculator, but we tend not to do that. If our decimal is 2.8, well, first of all, we know that 2.8 equals 28 over 10. we can simplify that and divide by 2 on both sides. 14 over 5. And then the reciprocal of that, well, it's just 5 over 14. And that is simple stuff. If you want to convert this back into a decimal, you can just convert it like so, or you can use a calculator. Next we have prime numbers. Prime numbers are numbers that can only be divided by themselves and 1. Now, we know 1 is not considered a prime number. 2 can only be divided by 2 and 1, so it's a prime number. 3 can only be divided by 3 and 1, so again it's a prime number. 4 can be divided by 2 as well, because 4 divided by 2 gives 2 with no remainder, so therefore 4 is not a prime number. 5 can only be divided by 5 and 1. Hope you get the idea. 6 is not a prime number. 7 is a prime number. 8 is not a prime number. 9 is not a prime number. And apart from 2, we know that all even numbers except 2 cannot be prime because they can be divided by 2. If we look at the first few prime numbers, we have 2, 3, 5, 7, 11, 13, 17, 19, not 21, 23, not 27, 29, 31, and we can continue all day because there is an infinite number of prime numbers. The unique factorization theorem states that any number can be uniquely represented by a product of its prime factors. Well, that sounds like a lot of words. If we have the number, say, 64, well, 64 is the same as 2 times 32. 32 is the same as 4 times 8. 4 is the same as 2 times 2. 8 is the same as 4 times 2, which is 2, 2. And we can circle the prime factors of this number. And we can say here 64 equals 2 times 2 times 2 times 2 times 2 times 2, which shortens down to 2 to the power of 6. Now 64 has only got 2 as its prime factor. 64 is a power of 2. If we have a different number, say 72, well, 72 is the same as 12 times 6. 12 is the same as 3 times 4. 3 is a prime factor. 6 is the same as 2 times 3. 2 and 3 are prime factors, and we have a 2 here and a 2 here. So we can say 72 equals 2 to the power of 1, 2, 3 times 3 to the power of 2. And that is representing 72 as a product of its prime factors. The unique factorization theorem is saying that each number can be represented uniquely as the product of its prime factors. Say we have two numbers, and these numbers are 3 and 7. We can look at the multiples of 3. The multiples of 3 are just 3 times an integer, so 3 times 0. Well, 3 times 0 is 0, but we tend not to look at that when we're looking at lowest common multiples, highest common factors and stuff like that. So we tend to start with 3. The next multiple of 3 is 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, and we can continue that. 7 is 7, 14, 21, 28, 35, 42, 49, and we could continue that. Now, the lowest common multiple here is the lowest multiple that occurs in both numbers. Now the lowest common multiple that occurs in both numbers, it's not 3, it's not 7, it's not 6 or 14. We're looking for a number that occurs in both of them. Now 21 occurs in both of them, 42 occurs in both of them. So we know that 21 and 42 are common multiples of 3 and 7. A common multiple. Now you see what a common multiple is. The lowest common multiple, or the LCM, is the lowest common multiple, which is just 21. Now this is important for, you'll get questions such as like, one train leaves, it stops at every 3 stations, and another train leaves and it stops at every 7 stations. A bit unrealistic, I know. And you want to see when the trains, what's the first station at which both trains stop, and that station would be the 21st station. Another key term is the highest common factor. Let's just write that, highest common factor. Now say we have the two numbers 27 and we have the number 32. We can draw a prime factor tree for each one, just as we did previously. It's called a prime factor tree. 27 is the same as 3 times 9. 9 is the same as 3 times 3. Those are our prime factors. 32 is the same as 2 times 16, and it's the same as 4 times 4, which is 2 times 2, 2 times 2. We can circle the prime factors. 27 equals 3 to the power of 3, and 32 equals 2 to the power of 5. Now, so 27 is a power of 3, and 32 is a power of 2. We have no common factors between these two terms. Therefore, our highest common factor is simply 1, because 1 can be divided into both numbers. However, if we have the two numbers, say 40 and 72, 40 is the same as, do it here, 40 is the same as 8 times 5, and 8 is the same as 2 times 2 times 2. Those are our prime factors. So 40 is the same as 2 times 3, 2 to the power of 3, sorry, times 5. 72, well, 72 is 6 times 12. The 6 can be split up into 2 times 3. This is 3 times 4. 4 is 2 times 2. So we know that 72 is the same as 2 to the power of 3 times 3 squared. The highest common factor between these two is, well, what is the highest power that is prevalent in both numbers? The highest power of a specific base. Well, if we look at 2, we can see that 2 to the power of 3 is in both numbers. A common factor, the highest common factor is 2 to the power of 3, because we have not got any other common factor apart from, of course, 2 to the power of 1, 1, and 2 to the power of 2. But we're looking for the highest common factor, and that is 2 to the power of 3. If our numbers were 120 and 72, well, 120 is 2 to the power of 3 times 3 times 5, and you can do that using the prime factor tree, and 72 is 2 to the power of 3 times 3 squared. Now the highest common factor is different. We look at the 2's, the highest common factor between them is 2 to the power of 3. We look at the 3's, well, now the highest common factor is just 3 to the power of 1, and that's a 1 that you don't need to write, so it's just 3. Then we look at the 5's, well, we don't have a 5 in 72, so the highest common factor is just 1, or in fact you don't need to write anything there. So then we look at this, 2 to the power of 3 times 3, and that is your HCF, highest common factor, which you can write as 8 times 3 equals 24 if you like. Now if we continue with that example, if we have 120 and 72, we know that 120 equals 2 to the power of 3 times 3 times 5, and 72 equals 2 to the power of 3 times 3 squared. And we know the HCF, the highest common factor, is 2 to the power of 3 times 3, which is 24. If we were to find the lowest common multiple, we can do this by looking at these numbers. The lowest common multiple is given by multiplying the highest power of each prime factor across both numbers. The highest power across them for 2 is just a 3, because that is the highest power we have of 2 in both 120 and 72. Then when we come to the 3, the highest power we have is 3 squared. And when we come to the 5, the highest power we have is 1, just 5 to the 1. And your LCM is given by that, so that is 8 times 9 times 5, which is 40 times 9, 360. That is your lowest common multiple of 120 and 72. Finally, for this video, we have the product rule for counting. The product rule for counting. The product rule for counting is quite simple. Say we have a restaurant, you're going to the restaurant and you have to eat a starter, a main meal, and you have desserts. Well, our starter, say we have starters A, B and C, and say we have main courses D, E and F, and desserts G and H. Well, that means we can pick from 3 different starters, 3 different main meals, and 2 different desserts. So for example, we could have A, E and H, we could have A, D and H, we could have A, F and H, and then instead of A we could have B, E, H, A, D, H, B here, B, F, H. You know, we can choose whatever we like. We can have C, E, G, whatever you like. What's important is we have 3 options here, 3 options here, and 2 options here. So say we picked A for our starter. Then we still have 3 options for the main and 3 options for the dessert. And so we have A, and then we have D, E or F, then we have G or H. Well, the way to write down all the possible outcomes, all the potential combinations, is by multiplying them. Multiplying 3 choices for A for the starter, 3 choices for the main meal, and 2 choices for the dessert. And that gives you 18 different combinations. Sometimes it's more simple, sometimes it's less simple, but this is the product rule for counting. To work out the number of different combinations of some choices, you need to multiply the number of choices you have for each event, and that will give you the number of the total number of combinations. Another example to look at is a passcode. So if we have a passcode made out of 4 numbers, A, B, A, B, C, and D, Well, each of these can be between 0 and 9. So we could start at 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, all the way to 9, 9, 9, 9. Well, you could just say there are 10,000 numbers between 0 and 9999, or you could look at it by a listing strategy. Product rule for counting, where we have A, B, C, and D. Each of them have 10 different choices, 10 different possibilities, because there are 10 digits in our base 10 number system. And by the product rule for counting, we can say 10 times 10 times 10 times 10 gives us 10,000 different combinations. Now, we can tweak this question and say that we have A, B, C, D, and D is sort of broken, so we only have the numbers 2 or 3 for D, and the rest is still 0 to 9, 0 to 9, 0 to 9. It would be harder to look at it this way. It would be easier to look at it this way. A can still be 10 different numbers, B is still 10, C can still hold 10 different numbers, but D, well, it's a bit broken, so we can only have 2 or 3. Those are 2 different numbers. So by the product rule for counting, 10 times 10 times 10 times 2 is 2,000 different combinations you can have in that scenario. Thank you very much for watching. Please subscribe for more maths videos.